So this is the second set of worked examples for the gravitational potential energy lesson, and this one's dealing with the issue that we had when the force wasn't in the same plane as the direction travelled or the distance travelled. So here we've got a situation where we're pulling a concrete block along the floor. We've got 400 Newton force, an angle of 42 degrees to the horizontal, and we're trying to find out the work done when the block is dragged a certain distance along the floor. So the horizontal distance it's travelled is 30 meters. Now the first thing we need to do is find out how much of the force was in that same direction. So we split our force vector into two vectors, a horizontal and a vertical. So our horizontal force vector is going to be given by trigonometry. We've got a cosine of 42 degrees is going to be the adjacent over the hypotenuse, and so the adjacent is going to be given by 400 times by cos of 42 degrees. Now combining that with our work done equation, our work done is going to be force times distance travelled in the direction of the force, or in the same plane as the force, and that's going to equal 400 times by cos 42 times by our distance travelled, 30 meters. And we plug that in and we get 8,900 joules, or 8.9 kilojoules. So that's our first example. Let's have a look at our second one. This is to highlight that not only can energy be transferred from kinetic into gravitational, or gravitational into kinetic, you can also go into plain old work done. So we can have situations where kinetic energy transfers into work done to friction, say, or in deforming an object. So here we've got a rugby player of mass 82 kilograms running at 7.5 meters per second. He slides along the ground, comes to a halt in a certain distance. So we could just draw this situation, I suppose. Got this chap here, he slides a distance of 5.6 meters, and he had a mass of 82 kilograms. He had a velocity of 7.5 meters per second. So we're trying to find out what was the force, the frictional force, acting on him when he was sliding. Now first thing to notice is that the frictional force isn't in the same direction that he's travelling as such. That's to the left, he's travelling to the right, but it is in the same plane, so that it is doing work. Perhaps when we defined the equation before with the distance travelled in the direction of the force, what we should have said is in the same plane as the force. So firstly we need to think about the energy transfer, and the energy transfer in this case is going to be kinetic energy into the frictional force, work done. Work done by the frictional force. So here, and I suppose you could consider that as being heat or something else, but we're just going to say the work done by the frictional force. So we essentially end up with two equations. We've got the equation for kinetic energy, half mv squared, and that's going to equal the equation for work done, which is force times distance travelled. This force here being the frictional force, and the distance travelled being the distance travelled in the same plane as that force. So luckily we've got a bit of information about his mass and his velocity, which allows us to calculate the kinetic energy. So if we rearrange for F, we're going to get the kinetic energy, half mv squared, divided by our distance d. So plugging in a few of our values, we've got 82 times 7.5 squared, and on the bottom, taking that half down to the bottom, we're going to have 2 times the distance, 5.6, and that's going to give us, if we plug that all into our calculator, it's going to give us an average frictional force of 410 newtons.